I believe it's time to spread out the latest and greatest from the Curious AI company. Go ahead.
Thank you, Timo. If you don't hear me back there, just start shouting. I'll try to fix my microphone. Okay. Is this better? Okay, now it's better now? Excellent. So next week I'm going to in ICML conference in New York. There's going to be a machine learning conference, and there's going to be a deep learning workshop. I'm an invited speaker, and I'm going to give you a rehearsal talk. The talk is not quite finished yet. I have still 1 week time to polish it, but I hope it's going to be okay. The intended audience is going to be deep learning people, mainly. So if you don't know deep learning, this is going to be a little bit deep end of the pool. But let's see, I hope there are nice videos and stuff, so even the people who don't know anything about deep learning can enjoy at least that part. So the topic of the workshop is how to make deep learning work in the regime of very little data. I'm going to focus on the case where there actually is a lot of data, but we only have few labels. This is a realistic case in many real-world problems. We have a little bit of labeled data and a lot of unsupervised data, unlabeled data. So think about, for instance, a lot of videos. We have a lot of video material. We can often collect a lot of raw sensory data. My thesis in the talk is that in order to make good use of unsupervised learning in these kinds of settings, is that we have to create a network which is able to clean and label its own data. Usually this is the task that humans do when they are labeling the data. They are selecting the right data points, and then they are labeling them. So I'm claiming that unsupervised learning can really only help if we can get those methods to do what humans are doing. So the big question is how? I'm going to divide this talk into 3 parts. First, I'm going to talk about the relevance. There has to be some task for which we are trying to tune unsupervised learning. Then I'm going to talk about abstraction hierarchies. The world is hierarchical, and we need to have models which are able to capture those hierarchies. And the last thing is a new thing, perceptual grouping. If I'm watching you out there, I can see many individual people, although you are occluding each other, and if I'm looking through the window, I can see the building out there, and I perceive it as a whole. And this is something that computers are not that good at doing yet. So, the first part, relevance. There's a Reddit page where people are asking questions that we are supposed to answer in the workshop. So this is one of those questions. How do we evaluate unsupervised learning? And my answer is there that obviously unsupervised learning is for a purpose. It's a tool. It's not a task for its own sake. So if we have some recognition task, classification task, then that's where we should evaluate unsupervised learning too. How much better can we classify if we take unlabeled samples? It's quite clear that different tasks require very different information. This is a picture from Times Square. It's where the conference is located. So if I'm trying to find the conference place, I'm paying attention to completely different cues, different types of information than if I'm trying to drive a car or if I'm trying to catch a cab, for instance. So unsupervised learning needs to take cues from the task that it's supposed to help in order for it to work. One of the things which human brain does, and this is also one of the questions that was posed in the Reddit thread, is what about unbalanced data? Often our unlabeled data do not capture quite the same distribution as what we are interested in. I mean, the task, for instance, if we are building a self-driving car, might be something where we are recording video from the car's perspective, and much of that video contains frames of empty road with forest and so on. And if we just learn that, that's not going to be very useful. Human brain modulates its own learning rate based on relevance. If we see something interesting, then there are some neuromodulators that are released, and that also enhances learning. So we have to take that into the system and modulate the learning rate in such a way that effectively the data set is much more interesting. So if you look at from the learning rate perspective, like which frames do we actually learn from, then they are the ones which contain somehow interesting information like cars, traffic signs, and so on. There has been a lot of work in attention, and this is a very important part of making these systems work. So if we not only pay attention to a particular time instance, but also particular features in the image, then that's going to help unsupervised learning focus on the features that are relevant. So this is an example of a recent paper from Xu et al., ICML last year, where you can see the pretty much state-of-the-art attention systems. There is a spotlight of attention. So that's about relevance. We have to pay attention to what the task really is, and I'm going to come back to that. But now, hierarchy. The world is hierarchical. So if you think of galaxy clusters and galaxies and solar systems and planets and cities and people and neurons and atoms and quarks, the whole world is hierarchical. Our brain captures that hierarchy. In 1965, neuroscientists David Hubel and Thorsten Wiesel discovered a hierarchical representation in the visual causes of a cat. And ever since that, we've known that we should do that in computers. This is basically what started deep learning more than half a century ago. They earned a Nobel Prize, that's nice, and now we have deep learning, that's also nice. Basically, the abstraction that we made for those neurons was rate coding. So real neurons, these are pyramidal neurons in the cortex, they are integrating a lot of information and they are spiking, they are firing action potentials. But that's difficult for engineers. So we abstract fast and less fast spiking by rate coding. So just fast or slow, big value, small value. So our current neural networks look a little bit like this figure. The activations in the big layers are represented by simple numbers. Then if we look at the hierarchical models, some of the best working hierarchical models in theory are hierarchical latent variable models. One way or another, most of these systems that are in use capture the same principles. So let's look at how a hierarchical latent variable model works. there is we postulate a hierarchy of representations, and then we start looking at how does that model capture the prior probability of observations in the world. So imagine that you would have to randomly sample natural images, for instance. The way the hierarchical latent variable models work is that they start, this is an example of a directed graph, you start randomizing, you select randomly some values at the higher level, and they have some kind of abstract meaning. For instance, that this is related to cars. And then once you have those numbers, those variables, latent variables selected, those define the probability, those change the probabilities of the lower layer. So if it's about cars, then certain types of observations in the world are more probable. Then we select, we randomize again, we pick random numbers from that distribution, and now we are at lower level of abstraction, so it's a little bit more detailed. We continue this. Again, the higher levels describe what's the probabilities at the lower level. We sample from that distribution, and we get even more detailed things. Oh, sorry. I'm practicing this talk still, so now I lost my my car. There was supposed to be a car that came as a result. Okay, anyway, this model defines the prior over the whole world. So if you take a different random shuffle from that, you get a different picture. And you can repeat this over and over again. In principle, this is a perfect model for everything that you can see in the world. Now, the difficult part with these models, well, there are two things, inference and learning. The problem during inference is that once you actually see an observation like a car, how do you know which latent variables were actually responsible for that? And the solution is given by Bayesian probability calculus. So starting from the observation, we have likelihoods going upwards in the model, and then they are matched with the priors flowing top down, and together these form the posterior. The Bayesian probability theory tells exactly how this works. Unfortunately, it's extremely hard. In principle, we have to model the posterior over everything. It's a very, very high dimensional space, probability space, and we have to model the probability of every possible thing. That's intractable in practice. Learning is fairly simple. Once we have the posterior, we just tune the model so that the prior model so that it matches better what the posterior was. So that next time when we sample from this model, it's more likely to give us a sample that we actually observed. This is intractable. So in practice, we resort to so-called black box inference. This is, for instance, what supervised learning does. Nice thing about this is that you don't have to specify exactly what is the causal structure of the world. We're only interested in the inference part. We see a picture and we want to understand this is a car. In physics, causality doesn't actually go from top to down. It's not like galaxies somehow cause the interaction between quarks. No, it's lateral interactions in every level of the hierarchy. And for instance, these directed graphs cannot really model that. There are other models like Boltzmann machines which can easily represent that, but we don't really want to know exactly what kind of causalities there are. We just want to get to the end result. And that's black box inference. We somehow take inputs and we just do whatever it takes. And we typically learn that. We do whatever it takes to come up with the posterior, with the final conclusions. Now, one of the questions that was posed was that, okay, how about these Bayesian methods? Often people identify Bayesian methods with sampling. So if we somehow throw random samples, then that's Bayesian. But in fact, Bayes does not play dice. Inference, optimal inference, represents the whole posterior. There's nothing about sampling. So if we think of supervised learning, normal supervised learning, for instance, that can be seen as Bayesian inference. It's just black box inference. Even though there's nothing like sampling, it's still a valid Bayesian inference procedure. In fact, any system that can do something sensible is bound to be Bayesian. It doesn't need to be sampling. So our normal deep learning, supervised learning is Bayesian inference, but it only looks at this inference part. It doesn't look at the generation. If we want to use unsupervised learning, then typically we want to look at how well our model can represent our inputs, because that's how we learn. And that's where we get to autoencoders. So we take the normal supervised part, and that's a little bit like the posterior inference, and then we add another model, which is like the generative model. The autoencoder has a limited number of neurons at the highest layer, so it needs to pack things. And that's what forces it to learn a meaningful representation. Unfortunately, it's not very good. One of the things it's missing, it's not sensitive to anything else except the recognition of, or the reconstruction of the mean. So for instance, if there are two things which one of them has small variance and another one has high variance, when we are reconstructing stuff, we don't really know, or we are insensitive to these kinds of things. Another big problem is that in order to be able to reconstruct anything, we actually have to represent all the details too, because just knowing that it's a car is not enough for reconstruct anything. So autoencoder has two problems. One, it doesn't recognize anything except expected values, and then it suffocates to details. Denoising autoencoders solve the first problem. When we are giving the system a task of not reconstructing the data, but to denoise the data, it turns out that this actually makes the system sensitive to all kinds of information, not just the expected means. This still has the problem that all the details need to be represented at the highest layers, but last year we presented the ladder network, which solves this problem by imitating the computations that you would do in a hierarchical latent variable model. So the details can flow through skip connections from the encoder to decoder. This has had quite a lot of success, but there have also been some failures. So I'm going to go through them and then hopefully explain how we are going to fix the failure cases. Last year when we presented the ladder network, it was state of the art in a standard permutation invariant MNIST classification task. MNIST is a data set with handwritten digits, and our ladder network beat the previous state of the art quite significantly, particularly in semi-supervised tasks where you don't have all the labels available. Now, ladder is no longer state of the art, but very close. So there are some other techniques that can do somewhat similar things, but I'm not going to go into detail here. If we just look at the filters that develop in standard supervised deep learning systems, the filters at the first layer look, in a fully connected model, look somewhat like this. You can see that the filters capture some pieces of digits, maybe, but they are not fully localized. ConNets work much better, and they have very localized filters at the first layer. It's interesting that when we look at the filters that the ladder network develops, using also the denoising task at the, as an auxiliary task, it develops filters which are much more like those found in the ConNet. So if we compare them side by side, you can really see the difference. Another thing is that we've found is that these ladder networks really develop very nice hierarchy of invariant features. So this is something which we can count as successes. Then the failure. This is an artificial data set where we replicated that behavior. That if we have supervised learning task, where the error is decreasing as the number of samples, we can replicate that with the ladder network, except that this time those samples are unlabeled. Only 1,000 of them are labeled and the rest are unlabeled. So unlabeled samples are pretty much as valuable as labeled samples, which is really nice. However, what we have found is that if we make the task harder, so this basically has one object per sample, just like MNIST dataset. It has 1 digit per sample, and then it works. But if we add 2 objects, supervised learning gets much harder, so it requires more data to learn. But unfortunately, this semi-supervised learning fails miserably. So new samples no longer are valuable. We don't get any benefit from adding unlabeled samples to this. If we start from more labeled samples, of course the behavior is, the performance is better, but again, the unlabeled samples don't really give us any benefit. So this seems to indicate that what's happening is kind of self-labeling. Suppose that we have a large pool of unlabeled samples. It's this bluish thing, and then the light blue thing represents labeled samples. So once we start with those correctly labeled samples, effectively the network, in easy cases, is able to label a lot of the unlabeled samples. So it's able to gather learning information from them. And once it does that, once it can sort of label its own samples, it can use those samples to learn more, and it will be able to label even more samples, and so on and so forth. We get this kind of virtuous cycle that we effectively start labeling the whole data set of unlabeled samples, and then performance increases pretty much as a function of the number of unlabeled dataset size. In a more difficult case, however, of course we are still self-labeling some of the samples. But if we are not labeling enough of them, it might be that we are only labeling like 500 of them, and using those 500 we can label 250 more, and so on. When we keep doing that, we saturate. We can get a slight benefit, but it's not nearly as large as in the easier case. So it looks like these unsupervised learning techniques work really well when they can get to a certain level where they can start self-labeling their unlabeled dataset. In the real world, this may pose a problem because, of course, the world has many objects and it's difficult for the network to make sense out of that, particularly when it hasn't learned that much yet. So now we come to the last part of the talk, perceptual grouping. This is something that humans do really well. When I started in Teuvo Kohanen's lab more than 2 decades ago, Teuvo had on a wall kind of demonstration tool where you could pull a string, and then what happened is that, it was full of dots, and when you pulled the string, some of the dots moved. So I'll try to replicate this Teuvo's painting to you. Painting full of dots, and when you pull something, the dots start moving. So I hope that you notice there a pattern. It's probably, who saw something? Okay, so you are pretty good at this. This is a difficult task for computers. It also works if some of the dots are not moving, but they are colored differently. It might even work if they are of different shape. This might be difficult if you don't really see the dots clearly enough. Anyway, the whole point is that we do this perceptual grouping really well. So this is the type of picture that you might imagine that a computer vision system can handle. It's a frog, yes, we can detect that. But our brain does that much better than typical machine vision systems. And I think that we now have some ideas of how that works. Interestingly, just like the hierarchy was found in the brain more than half a century ago, this temporal coding that seems to underlie our ability to group things together was found in the brain in '87. So we've already known for quite a long time how that works in principle in the brain. So again, in the cat brain, these guys were recording neurons, and they found out that neurons that are coding for the same object are synchronized. So it looks something like this. And now we need to take a more expressive coding for neurons. It's no longer enough to just look at rate coding, because the synchrony carries information which is important for understanding the grouping. So let's go back to these pyramidal neurons that are firing action potentials. But now, let's not abstract that with rate coding, but let's keep the synchrony information there. So the idea is that those neurons that are synchronized together will fire together. So they are phase synchronized. So if we record from those different sites, the neurons that represent the same object, for instance, those green things here, fire all together. So they are part of the frog. There are some other groups that fire at different times, and this allows the brain to effectively process these things in parallel, using the same network, without any interference from other groups. Neurons have fairly short integration times, so if the neurons are not firing in the same phase, the neuron has already forgotten the input from the previous phase. So it really is able to clock rate varies. This is in so-called gamma range, which is from, say, 40 hertz to 90 hertz. I think people found some gamma oscillations in 60 hertz in the US, but they didn't want to publish that because that would have been the, you're just measuring the voltage from the from the wall. So they said that it's 40 hertz. That's something like 60, 50. In Europe, they don't want to report 50 hertz, but that's roughly.
Does it vary between different situations? Like if I have a certain clock rate at the moment, if I can go and walk.
Yeah, it varies, but I don't know if anybody knows how exactly it varies. What are the principles? So anyway, what this coding should allow us to do is, like, if we are looking at a natural scene, what this coding should enable us to do is to split this scene into different objects. And now what the brain does, it's seeing these different objects and it's making sense of all of them. So in some sense, the brain is reconstructing these objects. So we are seeing whole objects rather than objects with a lot of holes. And of course, the brain also needs to represent which parts of the object are actually visible. But it's easier to represent the whole objects and these masks, the black pixels here represent which pixels are actually visible. Because these masks are not independent, and for instance, the mask of the car is fairly simple to get by just taking the shape of the car minus the tree in front. So for instance, the Z buffer information could easily carry information about these masks. So the generation process that the brain would be using would be in the opposite direction. We start from complete objects and the masks, and now the mask pretty much means like which input neurons are synchronized with which group. Then the generation process would tell the brain that I'm seeing these pixels from each object, and in total it makes a complete object like that. So now we wanted to see whether we could make a computer system that can do the same thing. We created a data set having the same kind of structure. We took some, again, MNIST is a nice data set. Everybody is abusing it for making all kinds of test data sets, so we did that too. We took 2 MNIST digits and shifted them a little bit, so there's a 3 and there's a 1, and then a background. The 1 has missing pixels because 3 is on top of it. So then we then we see which pixels are visible from each texture, and then that's the final picture. It's maybe hard for you to see. If you squint your eyes, maybe you can see better. It's a fairly difficult perceptual grouping task. We tested human ability to recognize the digits in these objects. There are some guys in the audience, so please raise your hands, that have suffered this task. I'm not going to tell who it was, but the best human managed to recognize 30% of the digits. It's really hard. I don't know how well you would be doing. And it takes a lot of training. 30% error rate. That was the best. Yeah, sorry. It takes a lot of training to get to that. and you can only do this like 15 minutes in a row, and then you need to have a break. So we developed a system that can handle this. This is a collaboration between Lugano and Helsinki. So Klaus Greff has been visiting Helsinki several times during this year, and we've been working on this thing. So what we did was let me explain how we did it. So we start from a denoising autoencoder. We could start from complete black box inference, but of course that's not going to solve the problem. So we have to relax the black box assumption a little bit. We have to give the system the right tools which it can make, with which it can make this kind of grouping. One thing that we do, if we think of these time slots that the brain is using oscillating neurons and then different time slots for different neurons. What we do, instead of oscillating neurons, we do parallel evaluations with the same network. So basically, we take all the different time slots that belong together and put them through one network. So the same network. So one evaluation for each group. It's the same network all the time, but we are evaluating it with different inputs. So that's one piece that we are going, one ingredient that we are going to put in here. Another thing is that in order to really come up with this, like how do you split the objects? You have to make sense of what is the reconstructed object. If you can do that, then it's fairly easy to figure out what is the mask. And if you know what is the mask, then it's fairly easy to improve the reconstruction of the underlying object. So in order to do that, we have to actually iterate. It's not really possible to solve this problem in one go. And this is also what the brain does. So we are using the ability of denoising autoencoders, the ladder network, to reconstruct its inputs. That's how we are going to fill in, for instance, the missing pixels of a car, or the missing pixels of these MNIST digits. So let's see how it works. We start with randomly initialized masks. That's the row on the right, and each one of these, it's a column on the right, and each row corresponds to one group. So we just postulate 4 groups. There might be 4 objects. Let's see how many there are. We postulate 4 objects, and then we start with just blank reconstruction for each one of them, so just gray. Then what we are going to do is we are going to compute the likelihood terms, so the terms that flow from the data. Now we are going to show the network corrupted data point, and then we are going to see what are the errors that each group is making. So that's the third column. Each network, each group gets this error information only from the pixels that it's representing. So it's masked. Every one of them gets a different error signal because they have different masks. The fourth column is the likelihood of different masks, but because the reconstructions are all the same, then all the likelihoods are going to be the same. There's no information in the reconstructions yet to tell what could the masks be. Then we are going to feed this in a parametric network, and we are trained the network to denoise in such a way that it comes up with better estimates. So the network comes up with better reconstruction for each group and somewhat better mask. Now, as you can see, the masks are not good at all at this stage. The last one, the red group, has now managed to reconstruct somewhat the background already. These masks are put through softmax because we know that each pixel is represented by just one group. So the masks have to sum up over pixels. Oh, sorry, over groups. For each pixel, the masks sum up to 1. So we put it through a softmax, which in this case, during the first iteration, gives us these masks. So now what the network is saying is that the reconstruction of the input looks slightly, look like the one in the middle. And then, because we know in denoising autoencoders, we know the ground truth, we can compare those two and then backpropagate the error signals so that the network will learn to do a better task next time. In here, I showed the reconstruction as an expected value, but actually each group is telling a different thing. So if one group is saying it's a black pixel, another group is saying it's a white pixel, then if the pixel actually is gray, then both groups know that it's a mistake. So the output of this system is a distribution, it's not just a mean. Anyway, now what we do, we iterate, because this problem cannot be solved on one go. So now we start with, previously we had just blank reconstruction, now we have something there. And previously we had random masks, now we have something in there. And we again have a look at the corrupted data and we calculate what kind of errors are different groups making. And the groups only see the error in the area where the mask is active for that group. This time now also the fourth column, which is the likelihood of a particular pixel being generated by this mask, that already has information now. Then we iterate again. We put each one of these through the same network and we get a better estimate. And then we put the mask through softmax. We repeat this. These are the likelihood terms. We put it through the network, and very quickly the network comes up with a representation which actually makes a lot of sense. So the network is able to not only reconstruct what are the underlying textures, but also it's making a very nice reconstruction of the mask. So the reason why the network is doing this is because when you split the problem into these individual problems, then it's easier to denoise. And in this case, you can see that the magenta group wasn't used at all. So we gave it 4 groups, it decided to use 3 groups. So it's very nice, fast convergence. And this is something that I don't think anybody else has managed to do so far. So this is the first time we have a system that's able to do perceptual grouping. We call this overall framework the tag framework, because we are kind of adding tags to these activations. It comes from iterative amortized grouping, so it's a backronym. And when we use the tag framework with the ladder, we call that the tagger. So now that's the tagger network. Since the ladder network has an encoder which is able to do supervised learning, classification, we can also train this system to classify. So here we trained a classifier which was given information just that there is an 8 and there is a 9, and that was all the information it used for making these classifications, but it learns that some of the groups don't represent any digit. We actually gave it not 10 outputs, but 11, so that one of the outputs could tell that, no, this is not a number. So the network really is able to not only split this input into constituent parts, but also recognize them. And if we compare this now in just one digit textured, then we can see that the fully connected ladder network is doing a decent job in semi-supervised learning. So if we have 50,000 labels, it works nice. If we have just 1,000 labels, then the ladder network is actually able to beat a convolutional network in this case, even though the ladder network we use is fully connected. So it's quite impressive performance, but the tagger network really excels in this task. It gets to about 10% error rate, which is what humans get in this task if we have just one digit. And it's competitive with convolutional network if we have 50,000 labels. If we have 2 textured image digits, which is the even more difficult case where humans get like 30% error, the tagger gets below 8%, which is much better than ConNet. And we really try to tune the ConNet. And in 1K, so if we only have 1,000 labeled samples, the tagger is really the only system that really is able to make good use of its unlabeled samples. And the reason why it's doing it, I claim, is that because it's able to clean its own input so nicely. It understands its input in a much better way than all the others. So we can do funny things with this. One of the things this network does nicely is that in some sense it's seeing behind objects. If we take this split representation of things where we have reconstructions of the texture that's occluded, and we erase some of the groups, and then we renormalize the masks because they have to sum up to 1, we can see that not only the network is able to see what's the underlying texture, it is making a very good guess of what's the underlying mask. So if I would remove the 9, then below that I would see an 8. So I think this is something that when we scale this up to natural images and so on would be a very nice tool for computer graphics people. You can just click an object, remove it, and we have just rewritten the history. This would have been a perfect tool for Soviet-era editors. It works for other datasets too. This is a shapes dataset which some other people have been using. We have color-coded here the different groups, and you can see that the network is really able to make sense out of these objects. The dataset has just rectangles and triangles. And on the very right, you can see that even if we trained this with three objects, even if we give it 4 objects, it's still able to do it. So it learns really nice model for the world. So I claim that this is really important for unsupervised learning. But not only that, I think this is going to be very important for future of AI in general. There are many things that we cannot yet do very well with deep learning and so on. But if you think, for instance, I showed the attention thing previously. our ancestors learned to detect a lion in the bushes very, very quickly. And us humans can now use that ability to detect cars in the bushes and so on. But if we pay attention to the car, it's not like we pay attention to this general area, but we pay attention to the car, an object. So attention clearly should benefit from grouping, because then if we pay attention to one part of the car, then transitively, because other parts are also part of the car, then we should be paying attention to those things also. I think one of the most interesting thing, though, like for future, would be hierarchical grouping. So imagine you watching a video, and now we are some layer of a deep learning network. This is roughly what that activation in that network would look like. So who understood what's happening in this video? Anybody? Okay. So it becomes much easier if we have a grouped representation. Now we can really see something, and there's an object, there are many objects. What's missing still, though, is that these objects also have interactions. So this is the underlying ground truth video. You may have spotted the car and the bicycle, but what you didn't maybe realize is that there was an interaction between the underlying objects. So the way this should be represented by a network, I think, is by a hierarchy of these tagger modules, that higher levels can represent the interactions between lower level objects. I think this is the way that neural networks will be able to go into the realm of symbol manipulation, reasoning, and thinking. So I think this is the future of AI. So, to summarize, I claim that to make unsupervised learning work, the network has to clean and label its own data. And I hope that you are kind of convinced with me that not only relevance and abstraction hierarchies are important, but perceptual grouping is one of the most important topics that we still need to solve in AI. And I think that we are making good progress there. Thank you. Sorry for taking a little bit over time. I hope it was entertaining still. Oh, I have some chocolates. Thank you. Any questions, or shall we start the informal discussion session?
Thank you, Harri. I guess we'll take a few questions, and then there's free association for everybody for a few minutes still.
What I still should mention is that the relevant paper is going to be in archive maybe next week. The code will also be available, so you can play around with perceptual grouping yourself.